In this video, I'm just going to review some of the techniques from BC to do integrals, and I'm going to do that through some sample multiple choice questions. So the first one, sine to the fourth of x times cosine of x. Now, it's important to know that this is, first of all, not just a standard undo a derivative type problem. The reason I know that is I've got a product. And when you have a product of two things, you should first of all think substitution. Your next step would be integration by parts if substitution won't work. But in this case, if I could maybe even think of rewriting this integral, maybe let me kind of do it my work off to the side here. Okay, I could rewrite this integral as the sine of x to the fourth and then cosine of x dx. And as I said, your first thought really when you see a product should be substitution. And what we're looking for is we have two functions, in this case a product. If I take one of the functions and I make it u, would the derivative of that function help me eliminate the other? So in this case, if I had u as sine and du, well, the derivative of sine is cosine, you see that I'm able to take out this entire piece and replace it with just a du. So my integral would become u to the fourth du. Now, sometimes people will say, well, why not cosine? Well, if I made u cosine, du would be negative sine dx, and this is being raised to the fourth power. I don't know how to deal with a du to the fourth power. A u to the fourth I can deal with. That's what we're aiming for. So in this case now, the antiderivative of u to the fourth, of course, is 1/5 u to the fifth plus c, and I plugged sine back in, I get 1/5 sine of x to the fifth plus c. So I'm looking for a 1/5 and a sine raised to the fifth, so the answer is B. Okay? Substitution is what you should be looking for first. If substitution won't work, then go to integration by parts. And let me clarify that. I mean when there's a product. Certainly if it wasn't a product and you could use some just method of doing, going against the power rule or undoing the power rule, do that. But if it's a product, I'd look to do substitution first. So in this example, we've got two big functions here. The sine of 2x, and that one, I guess the important thing here is to notice that you can split integrals, right, and have the sine of 2x dx plus, and now we've got, I'm going to put the 5 out front, we've got tangent squared and cosecant squared. I'm running out of room for my dx. Okay. Now, in this first example, I would make u 2x so that du is 2 dx. And this one is kind of a different example in that it doesn't look like there's a product, but it is a composition. So I do want to make sure I see that it's going to be 1/2 times the integral of the sine of u du. The antiderivative of sine is negative cosine. We could put the 2x back in. Okay. Now I haven't even dealt with this other integral yet, but I should be at least looking for a negative 1/2 cosine 2x. So let's start by doing some eliminating of ones that don't have that. So you can see already we're down quite a few. Okay. Now, something that we don't deal with very often is looking at the trig identities and looking at some things we could maybe simplify with trig. So let me just write down here that tangent squared times cosecant squared. Well, tangent is the same as sine over cosine. So tangent must be sine squared over cosine squared. Cosecant is 1 over sine, so this must be 1 over sine squared. And sine squared divided by sine squared is gone, and I end up with just 1 over cosine squared, which is secant. squared. So I could rewrite this integral as 5 times the integral of secant squared. And the antiderivative of secant is tangent. So that leaves me with A as my answer. Okay. We don't often make you do that, and really what I wanted to show you with this example was the substitution on the first part and how we could use that to eliminate a lot of things. But worth noting that there are some other ways you can do integrals other than just hammering out integration by parts or integration by substitution. And lastly, we've got this. We've got the derivative of an integral. Now, derivatives of an integral, remember, derivatives and integrals are really like inverse operations of each other in that they undo each other. So a derivative and an integral should cancel each other out, but we have this exception of a t to the fourth where we end up plugging t to the fourth in for x, and then we have to multiply by the derivative of t to the fourth, which of course is 4t cubed. And the reason we have to do that is chain rule. If you actually can imagine doing this, find the antiderivative. Okay, let's say you did that. And you don't know how to do that one for this, or do the antiderivative of this, but imagine you did, and you plugged in t to the fourth, and then you plugged in 2, and then you found the derivative. Well, you've put t to the fourth into this antiderivative, so when you find the derivative, it's a composition, and you have to do chain rule. Okay, and a way to think about this is like, let's say the antiderivative was big F of x, and we're evaluating at t to the fourth and 2. Okay, so f of t to the fourth minus f of 2. So when I find the derivative of this, if I say, well, I'm finding the derivative of everything. So the derivative of this, well, the derivative of f of 2, since f of 2 would be a constant, the derivative of is 0, and the derivative of this composition would be f prime of t to the fourth times 4t cubed. And this should be the original function. So that's kind of the long explanation for why it's got to be d. Remember that you have to plug in the bound and multiply by the derivative of the bound when you are doing the derivative of an integral. And it's all because of chain rule.